Architectural framework for data analysis Lena. Lena is a great Siberian river, so you'll see several photos of that. And architecture has many definitions. It defines the most important decisions in your program. And when I was finishing my master thesis, I had several thousand of lines of codes, and then at some moment I could not write any more line because everything else was just broken. And it was extremely hard, and that's how I started learning more about object-oriented programming, functional programming, and think about maintainability and extensibility. An architectural framework, it tells you how to write your program. And it's not a library where you just take the functions you need, but it makes more requirements for that. And there are architectural frameworks in web programming which are Django and Flask, and they are extremely well written and very useful to users. And I was looking for an architectural framework in data analysis, and I didn't find 5 years ago. So I tried to make one. And the plan of this talk is I'll tell you about the 3 ideas behind Lena: sequences and elements, lazy evaluation, context, and template rendering. Then I'll tell about applying several algorithms in one pass, like both in parallel, then how sequences can be reused, and some metaprogramming. So a sequence. We can put one element into a sequence, just a lambda, Pythonic lambda. So we have some data, and we can run the sequence on the data and get results, but we need to materialize them in a list because it is lazily evaluated. So we can combine sequences. So we have a source, which is a sequence which doesn't accept any input. You run it like this. Then you can put our previous sequence into this sequence. Then you can put another several elements. For example, you can slice it take first million events from this flow, apply some other functions, and get some sum. So in the end, you get this value. And here it is only one value, but it's more general when we assume that we can have many values because it's easier to generalize. So I said about lazy evaluation, and the thing is that instead of return, you use yield, and you can use it several times in one generator. So we have this class with a method called run, and it accepts a flow. A flow is also some generator or some iterable. So you iterate it, make some analysis, and calculate the sum, and yield some results. And lazy evaluation, it means that the data processing is done for every step by step. So it doesn't wait until your full data is read. And this could be good for speed. For example, when you have like slow input output, when you finish reading all data, you already have processed everything. And also it's good for scalability because some data, they just don't fit into memory, and you have to either make some special steps or your program will just crash, and it happens sometimes. So with this, you can scale it to big data. And okay, it was one of the key features. So the next one is template. So PyHEP.dev. So this is a standard standalone TKZ script. It's almost like LaTeX, but you just have TKZ picture environment here. And here it is, I say it's a template because this variable is rendered from context. I'll tell a bit more about this. Yeah, but this is how it looks like. So I wanted to compare it to Matplotlib because many people use it, and it is imperative. I have this example from Matplotlib, which is imperative and not structured compared to the previous one. And the previous TKZ is declarative definition, and it feels very different, and it's also structured. Why I use it, because it's the best publication quality is because it's native to LaTeX. You have the same fonts and everything. Okay, yeah, you may change something, but when you put a matplotlib into an article, you usually see the difference, that it looks different from the text. That's why I call LaTeX publication quality. And also presentation quality, because people, they put plots into a view presentation, but then all these fonts, they change, they scale, and you often can't see anything on this. And it's not quality, I would say, but when you have one file for this, you can change the scale and all your fonts will be visible, and it's extremely easy and just useful. It was a bit separate from the architectural framework, but I wanted to tell about this. What I actually use is a template, so we can have a block for header. This you can import something or do something. Okay, you can have variables in a template. Then you have so a context is just a dictionary. You have it available, and you can take a key variable at a name, and then you may have unit. If you have this unit, you can add this unit to the X label, and yeah, you have these blocks. So it's like very flexible, because you can have different names with the same template. And about template rendering, so Jinja is extremely used. It supports variable cycles, branches, like if template inheritance, so you can take a part of your plot and use it in another plot from the template. And but I mostly do it because presentation is separated from structure. I don't have to like make analysis in one function and make plotting in the same function. So it's good that the drawing logic is separate. And we can adjust our template for many plots that it. We can reuse them, but we need to provide context for this. But this is also metadata, which we all also need. So this is an example real analysis class. So we just read data from a file. We get file names from the flow, just for generality. And then we yield some data from this file. We can also yield a data plus context. And context is just a dictionary, as I said. And we can have this data type Monte Carlo, for example, or data. And when we read this, this will go to context, and it will pass through the whole sequence until we render LaTeX here, for example. And in this element, we will have a different color, for example, for Monte Carlo or for data. And what we do, so all these elements, they are decoupled from each other. They don't know anything about each other, but they have this common flow with context, and they can add something to context. For example, we add file name, which is output file name. We added X here, and we transform this histogram to CSV, write it, then render LaTeX from template, write this rendered LaTeX, and then we convert this LaTeX to PDF. And if we want, we can also convert it to PNG. This is just general. I mean, you don't have to use everything on this, because as I said, all these elements, they are independent of another. And yeah, and we get results by just materializing the list. And when they are decoupled, it's very easy for development, because we can print the flow at any point, what we read here, what we read there. We can take the first 1,000 values just to make like preliminary analysis to test that our basic analysis work. We can also insert some cache. For example, here we fill the histogram, but next time we don't want to recompute all the previous things. And if we have cache, we just use this cache. We can also put the end here, for example, on the server. I don't make this histogram transformations. I only make a cache and transform it to my computer. Yeah, of course. Yeah, and if you don't need this, you just comment it. So it's really easy, and you don't have to edit any of your classes. You wrote this read data and you just use it. So as I say, that's why it's easy for development. And also there are some optimizations. For example, when we read this histogram to CSV, we have this data, we have this template, and if we can see that the template or data did not change, that we don't reproduce this LaTeX because it takes quite some time to make every LaTeX plot. So we can skip it if we don't need it. And this is tracked automatically through context. So this is one of the first benefits of this framework. So it doesn't reproduce every plot, only when it is needed. So I recall you some ideas. So we have some elements. The core element is lambda was an example. So it takes a value and returns another value. There is a run element, which has a method run. It takes a flow, which is a generator, and it is all the generator. So it is many to many. And we have a source element, which takes nothing, but just generates indefinite number of values. And from these elements, they can be put into sequences, which is a sequence, yeah, just any number of core or run elements, and we use it, run flow, or a source which has like the first element, it doesn't accept any flow, and it just, and then you can add a sequence after that. So some transformations, and you call it source. It's generated. So they are both generators here. Okay. So as I said, we have loose coupling, explicit data flow, and all control is from Python. And yeah, then the next step is how do we do several algorithms, because we made one histogram now, and we tried to make two histograms. For this, we need split. So we have this incoming flow from read events. Yeah, let's read some root file and get events with coordinates x, y, z, energy, etc. And we take x coordinate here, make histogram, and make file name different x. And here we take y and make file name y. So we have this split, but there is a problem that our previous element, it doesn't work with this, because this run element, it consumes the whole flow, and we don't control it. We can't do anything with this. That's why we need a different element, a new element, which is called fill compute. It's an analogy to a histogram. So we just fill it, and when everything was filled, the external element split, it calls its compute method, which is a generator. So the compute is pretty arbitrary name, but I just thought about that something could be computed. And when we have an element like this, we can use it in split. Yeah, and it's this split, it takes events and fills every sequence. And then after the input flow is over, it yields from every sequence. And here we also introduce variable because yeah, we can put this variable name and the function, how it works with event, and make file name from this variable name. So we don't need file name y, file name x, but just this variable name from context. So this is some context formatting here. I think we saw it with Luigi talk. There was also some formatting for output files with this braces, curly braces. And okay, and then these elements, they, as I said, they don't care about anything. They just transform every histogram. So for them, it doesn't matter how many histograms we had here. So we don't change anything here or here in the data reading. And then we have, okay, let's make more plots. We can have several coordinates, y, z, x, y, z, and then we have variables, for example, another variable for particles, For example, yeah, in double show we have double events, which is neutron, then positron, prompt, and delay. And for particles, I can use any key in a variable, and for me it's nice to have a LaTeX name. For example, for positron, and I set this type particle just for easier maintenance. And then then I have the same, but in split I put particle and coordinates, the function I showed before. And we can just iterate on these particles. And because we have a list in a split, we can add lists. So because we don't use any configuration, but we use Python code. That's why we can have this list constructs and everything from Python. Yeah. And O is the same, but already we have like 6 histograms because we have 3 coordinates for positron, 3 coordinates for neutron, and yeah. And we adjust our file name to have these different file names for positrons and for neutrons. We want them different. Yeah, so it's pretty easy. And we could adjust our template as well, but yeah, we could also leave it as it is. So we already make 6 histograms, but most of the code is the same. But we can also add some logarithms. Yeah, I hope. Yeah, sorry, it didn't fit up. So we can, to add logarithm, we can also take split. So if it is an empty sequence, it doesn't do anything. It just passes all the values it gets. And here in this sequence, we update our context with log y, which is used during template rendering. If we write it there, we say that let's make a logarithmic scale for y, but we also need to remember that we need different file names for different plots. That's why we use a suffix logs, and if in the future we make some file name, it adds this suffix from the previous context. Okay, and we change our coordinates like this. So we have this variable histogram. We can add logarithm. We can add y minimal y can be 0 or some better value, automatic one. So we want both sometimes. And this way we have like 20 histograms because this is times 2 and this is times 2. Yeah, we just, so it's allows like making many plots. And this is already something very good because me personally, as Fiona, or I don't like making plots. So when it is done separately from my analysis, I don't bother about this, and this is a great help for me. But what can we do more with sequences? As I said, they can be reusable. And for example, we have a detector and we have events in every coordinate of the detector. And let's see how our variable is analyzed for each coordinate. So for example, here we have a z variable, which is taken from the prompt event of the double event. And we have our analysis. In this case, this is just the variable the difference between prompt and delayed. And we put it into a root histogram because every element can be changed. You can use Lena histogram or root histogram. You can do whatever you want here. So, and this analysis, it runs for every, okay, in the end you get a histogram which contains your analysis, and it must be able to deeply copy this, and it runs this analysis for every bin, and you get this histogram with the results when you call compute. So so you can read the documentation about this split into bins. That's why I needed to implement a histogram for Lena, just for this general thing. Okay, this is the last part. This is about metaprogramming. So here I put this sequence like manually here, but we can also take it from Okay, this is a function which transforms our sequence, and it takes head, middle element, and tail, and it makes a new middle element and does something with the tail. And the idea here is, if we have a sequence, but we want to put a filter, like we want to analyze some subset of the data, and we want to make it like automatically, and that's why we add a filter here and put this filter name just to have different file names in the end. That's why we add it to the context. So this tail sequence, it knows that it must use some new data name, and yeah, we take this previous sequence, we transform it on split, yeah, and we get a new sequence, and we don't have to modify our original code at all. So, for example, if you want to quickly check something, change something, make some special analysis, you don't have to spoil your previous code. And this is really nice. But in general, metaprogramming is like not super good, but sometimes it's much easier and better. Yeah, so elements can be substituted and transformed. And another thing for performance. So say we have two sequences from elements and one and two elements. Yeah. And if the first k elements are equal, we can merge these sequences into one sequence, and then we split divergent tails. Not only two, but any arbitrary number of sequences. And that's what I use in my program. So I have two different scripts, but they basically read the same data. And then I make just very simple script to take these two complicated scripts, yeah, merge this data part, and they make different analysis, but with the same data, and I don't have to run like the whole data in the server. I can use it only once. And yeah, that's metaprogramming. But for this, you must be able to compare your elements. They have a comparison operator. You should write it. And lambdas, for example, they don't support it, unfortunately, in Python, but yeah, it's not hard. So the conclusion is that you can't make it much different, because if you want elements to be reusable and composable, they must be loosely coupled. They should not be like a single block of code, but they should not know about one another. And they should have a common interface, which is like data context, and a common interface, yeah, generator or code, or just single value information. And if you want metaprogramming, you need introspection for these elements. Yeah, because there are like workflows which take a script and get like some end results, but it doesn't introspect the script. So I think not everything can optimize it if you can't introspect. And Lena helps us to, it takes from data to final plots. So it's not some, I don't know, very special thing like only histogram, but it makes it from the beginning till the end. Helps the user. It decouples numeric analysis from plotting. One template for many plots, reusable and composable software. And your programs in the end, they are more structured and beautiful. And the status of this, it's published on GitHub and PyHEP. 90% test coverage. So there are several releases, but it's not much used. At least I don't know about it. So sometimes it's changing, but your elements almost don't change, because the structure of one or many to many, they stay the same. And this method which I showed, it's in development, so it's not available. But if you want this, you can write to me and you can make it faster. That's it. Thank you.
Thank you very much. I've got the feeling that you can build quite complex flows, overflows. So for example, what helped me with like Luigi was always a visualization of that. Is there something planned or is there already a visualization to visualize the whole flow and where it splits and reconnects?
Well, this is like, let's say, a bit personal code in the sense I want to see it myself. This is like a code, so I don't need some external program to do it, and I did not use anything. And the thing that, as you say, it can be like large, but I don't want. I try to make my analysis in different steps, because if it's too large, I feel there can be like errors, and I try to separate analysis and like or watch these intermediate plots for every part of the analysis and see what is going on. Yeah, so I don't need like, I need still to stay attached to the code.
Hi, thanks for the talk. Maybe just a quick question. How does a Lena sequence deal with the ordering of the elements? At some point, one of the comments was that the various elements are independent from one, or they do not need to know. It's kind of like pure functions in that sense. And I wondered, my instinct is that still ordering matters, but maybe you can elaborate a bit.
Yeah, absolutely. Ordering matters because the flow, it comes from top to bottom. So you read data, then you make transformation in this. What I mean that this histogram, for example, it doesn't know about any other elements. It just takes input and produces output. Yeah, but the sequence knows about them. In split, you can put it in any order because they are quite in parallel. But here it is exactly how it should go. You can't change anything here.
Okay, thank you.
Yeah, so do you have any examples of actual like physics analysis plots that to show? I mean, this is interesting, but what I mean, is your entire analysis team using this, or like, can you, or do you have like in the backup slides, do you have any like plots from your analysis that you made with this that we can see what it actually looks like?
No, sorry, I don't know. So I use it myself. I make plots with this, and as I said, in general, these TKZ plots, they look better than Matplotlib. That's why at least I didn't invest much time into Matplotlib to make them look similar. But I can show you my presentation from a DPG conference. Yeah, I have it in physics conference, but yeah, it's a good idea to put it here.
Any other questions, comments? Chairman.
So what I'm looking here is right now there's some sort of a voucher that used to be like subscription language or sort of like a workflow language, but within Python surely. Is there, how do you draw the line between what should be written in like a YAML form that you should load up and build the sequence versus having this be on Python for the user to define? Where's the line that you draw?
Sorry, I didn't understand your question. What is the line between this and what?
Well, because we could have something like this, we could also have it in YAML.
In demo? In demo?
YAML.
Okay. Yeah, this is exactly the thing that I want to use Python code. I don't want to use any YAML because, for example, here I can like concatenate strict. I don't know. These are just Python objects, and I make Python objects, and I don't think. I mean, how can I use an object in YAML? I don't know, because as I showed, these are like real pieces of code. So yeah, YAML is just structured language.
Well, I guess what I'm wondering, how does it work for analysis protection? Because at the end of the day, What we care about is being able to serialize the entire analysis so we understand what it's doing. Somewhat independent of the actual framework itself.
Well, I mean, if you have code, you must have code, because if you have a bug in your code somewhere, it doesn't matter how you serialize. That's why I have like my entire code in Git, and if I want, I can make a Git version for a specific version of code, but I don't serialize code. Yeah.
This came up before, because earlier we were talking about statistics, and there's the split between wanting to do things declaratively or as code. Here, you know, when you say YAML, you mean declarative, because if you can force things into YAML, then it has been described declaratively, and that has some features, like you can visualize it, like the I'm blanking on what we were visualizing. His PyHEP. Like we were visualizing some things there because it's more restricted. It's a JSON object. And there are advantages to each. I don't think we have all decided that we want everything to be completely declarative, and therefore it all goes into YAML. This is an example. I wanted to ask you if you're familiar with Haskell.
Yeah, it is, but
Yeah.
well, I learned it and then I didn't use it at all. So
Okay, but this is very much in line with Haskell.
yeah, this is actually functional programming. You can
Right.
do it in Python. Yeah.
Yeah, lazy functional programming, these sequences that are context dependent, these are monads. It's a whole world built up around that. Doing it, but you're doing it in Python.
Yeah, exactly, because there are more, it's easier for users and it's easier for me, and there are packages in Python.
Right, I mean, there's sort of a difference in my mind between what's making it easier for the user, but also what's making it easier to debug. There are lots of users who will use packages like this or frameworks like this, will write on some levels forgetting about it. But a serialization or something declarative means that you can kind of get a holistic overview and actually understand what they're trying to do without having to place, you know, basis.path, plan, import these common functions that they keep writing all over the place. That's something we running into an atlas, and it just makes it hard for, you know, experts like do you develop or maintain the framework to debug, because you would have to have all the Python environments, set everything up in order to understand how they're running it or what's causing them to break. So these have some sort of way to export a serialized format. You can get that overview much more quickly without having to set up your entire environment just to match what they're doing in order to debug. Right? It's like a maintenance issue or a debugging issue. It's something that's easy for you to use may not be easy to debug for you.
I can only comment that functional style is the best for debugging, because this class, for example, it only takes flow and it returns yields some flow, and you can use it separately. It's not integrated in any other library or framework, so you can take one element and test it. But for the sequences themselves, yeah, I don't know what you want to debug. So I tested, as I said, I have like 90% of test coverage of this project. So I don't know how serializing would help with testing, but testing is important here. And it's really supported. It's better than some object-oriented programming or some like big block of code, which you should test somehow entirely, and it's harder, especially when it has some side effects or anything.
Any other questions? Any last questions for Stop? Okay, if not, thank you very much.
Thank you.
So it's time for the break, and when we come back, we'll have a discussion. I don't remember where we stopped, but we can look it up. Yes.